Hi guys, welcome back to this session, Counter Part 2, Synchronous Counter. First of all, we'll see some of the main features of the Synchronous Counter. We already know that all flip-flops here are controlled by a common clock. In other words, the changes in the output occur in synchronization with the clock signal. The result of this synchronization is that all the individual output bits change their state at exactly the same time in response to the common clock signal. Because of this, there is no propagation delay and no ripple effect in case of synchronous counters. The main advantage is its operating frequency is much higher than the same range of asynchronous counters. As we have in asynchronous counter, we have also got various types of synchronous counters like up counter, down counter, up down counter, Bcd counters. In other words, it is called a decade counter, ring counters and Johnson counters. Here in this session of video, we'll be dealing with the synchronous up counter, down counter and finally the Bcd counters. Okay, so now coming to the 4-bit synchronous counter. So here we have a 4-bit synchronous counter. The circuit of a 4-bit synchronous counter is shown here. It starts to count from 0, that is the binary value 0, 0, 0, 0 and increment or count upwards to 15, that is the binary value 1, 1, 1, 1 and then start new counting cycle by getting reset. Okay, so next it can be seen from the circuit diagram that the external clock pulses are fed directly to each JK flip-flop. Each and every JK flip-flop, the external clock is given directly in the counter chain and that both and J inputs are tied together in the toggle mode. Here the first JK are tied and here also the JK are tied. Everywhere the J and K inputs are tied together. But only in the first flip-flop A, the LSB are connected to high, that is logic 1, allowing the flip-flop to toggle on every clock pulse. Okay, so only this first flip-flop is given to logical 1. Then the synchronous counter follows a predetermined sequence of states in response to common clock signal, advancing one state for each pulse. The JK flip-flop B is connected directly to the output QA of flip-flop A. Here the JA and KA are tied together and directly connected to QA of the first flip-flop and correspondingly the flip-flops C and D are driven from separate AND gates which are also supplied with signals from the input and output of the previous stage, because here only when last two bits are 1 and 1 then the third bit will advance to 4. So only after 3. So 3 for 3 QA and QB must be 1, 1. Only after that QC must advance to 1 for the correspondingly the last flip-flop also must respond 1 and only when all QA, QB, QC are all 1, then it will proceed to 8. Likewise it goes. The additional AND gates here generate the required logic for the JK inputs of the next stage. Okay. So now coming to the timing diagram. So here the points where the AND gate outputs are high are indicated by the shaded areas. Okay. So from this we can see that only when QA and QB are high, QC will go high. Okay. So here this is for the first AND gate. For the second AND gate, when QA, QB, QC both are high, then this QD will respond. That is only after count 0, 1, 1, 1, that is 7. The next number 8, binary 8 will come. Here also only when QA, QB are high, QC will respond. Likewise here, only when QA, QB, QC are high, this QD will respond. Okay. So this is how a 4-bit up counter works. Then we'll be dealing with the 4-bit down counter. So we all know a 4-bit synchronous down counter start to count from 15 and decrement or count downwards to 0. After that, it will again start a new counting cycle by getting reset. So the inputs here, as in the case of up counter, the first J and K inputs are tied together and maintained at high. Likewise, we have got 2 AND gates here and here. The only difference is here the AND gates are given the complemented or the inverted outputs of QA, QB here. Instead of QA and QB, QA bar and QB bar are given inputs to the first AND gate. Likewise, so here also instead of QC, QC bar is given as input to the second AND gate. This arrangement is done in order to get the count in descending order, right? Here, likewise. So when this is high, the next count goes. So the difference between the up counter and the down counter is, instead of taking the inputs for AND gate from QA, QB, QC, etc., the outputs are taken from the inverted outputs, QA bar, QB bar and QC bar. That is the only difference, and the counter will start counting from 15 and it will go up to 0, 0 and then again starts counting from 1, 1, 1, 1. Okay. Then coming to the decade counter, or it is otherwise called BCD counter. So we know decade counter can also be built by using synchronous binary counters to produce a counting sequence from 0 to 9. So the BCD numbers are 0 to 9. Okay. So in order to achieve this, a standard binary counter can be converted to a decade counter with the aid of some additional logic circuits, logic gates like these AND gates and OR gate here. The help of this additional logic to implement the desired state sequence. Here what we want to achieve is, after reaching the count of 1, 0, 0, 1, that is 9, the counter recycles back to 0, 0, 0, 0. Okay. So after 9, it has to proceed to 0 instead of proceeding to 10. So that is nothing but, that is the BCD sequence, right? It is also otherwise called a modulus 10 counter. So here we have got the timing diagram. We can observe that the QA toggles for each and every clock pulse of the external clock pulse. This QA toggles to each and every clock pulse of the external pulse. And QB alters to the next state when QA, this QA is equal to 1 and this QD is equal to 0. When QD is equal to 0, this QD bar is equal to 1. So only when these two are high, QA will alter its state. QB will alter its state. So QC alters on the next clock pulse every time when QA is equal to QB is equal to 1. Here, when QB is equal to 1 and QA is equal to 1, this QC will alter. That is for the count when QA is equal to 1 and QB is equal to 1. The next count should be 4, 1, 1, 1, 0, 0, right? So this is for this QC alters the next clock pulse every time when QA is equal to 1 and QB is equal to 1, QC will change its state, will alter its state. Okay. Next, the QD alters on the next clock pulse each and every time when QA is equal to 1, QB is equal to 1 and QC is equal to 1. This is nothing but it is count 7. So after count 7, it has to proceed to count 8, that is 1, 0, 0, 0. Either through this thing, either through this gate, or when QA is equal to 1 and QD is equal to 1. When the another condition is through this AND gate, when QD is equal to 1 and QA is equal to 1. This is because after this count 9, then the next output must be 0, 0, 0, 0. So that is for this case, for making this, again resenting this, we are making this arrangement, this gate, when QA is equal to 1 and QD is equal to 1, the QD will be altering. Okay, this is how a synchronous decade counter works. And then we have some advantages and uses of synchronous counter. So it has been listed here. You can go through this, and with this we finally come to the end of this 4th unit, sequential circuits. Okay, hope you all understand this video. Thank you. Bye bye.